Markov jump process.
Yeah.
Okay, so last day we started with perfectly audible.
Yeah.
So last day we were doing with the date and time, and it will be two-way process. Till this much we have done.
Yes.
Now today we will be continuing with that. So we were understanding the two-state Markov model. So what is that? Yeah. So here there will be two things. Imagine a simple wall. Imagine a simple wall, and where a person can be in only two states. So a person can be two states, and I told you the two states being alive or death. So this setup is called basically your two-state Markov model, where what we will see, the transition from alive to dead. Okay, so it happens with a certain probability. So with this there is associated some probability. Now there is no coming back from death to alive, that you have to remember. There is no coming back from death to alive. So what we now want to determine? So here we want to determine the probability. What is the probability? That a person who is alive at age X will still be alive at age X plus. So this probability is called the T-year survival probability. Which is denoted as TPX, being P, that is alive at age X, plus T, given alive at age X. So here we can derive the mathematical derivation of the survival probability. So the mathematical, till this clear?
Yeah.
Mathematical derivation of survival probability. So that is how. So the survival probability is linked to something that is being called the force of mortality. So you can denote it as mu of X. So that is which represents the instantaneous rate of dying at age X. So if you say for the general case, so that will be TPX exponent of minus of 0 to t, mu of x plus s dx. This is plus. So what we mean by this? Here we mean we integrate the force of mortality mu. And what is the time interval? The time interval being 0 and t. That is the time interval. Now, what next we have to do? This is step. Then we exponentiate it with a negative sign, which makes it decay over time. Which makes it decay over time. So here, the larger mu of x, so that means the faster the survival probability declines. That side it is perfectly clear, screen
Yes.
and voice. Okay. So you can say there might be a special case. Okay. So what can be? So constant force of mortality. So if you consider special case, that can be constant force of mortality. So that means if we assume that mu of x is constant, so that means it does not change with age. It does not changes with age. So then the formula will be T of px is E of minus mu t. So that you can totally understand that this is following an exponential distribution. So what does that mean? It means, so consequences in the sense, suppose if mu is large, that means survival probability decreases faster. Survival probability decreases faster. Okay. So higher mortality rate. Higher mortality rate. And if it's the opposite, that is if mu is small, so the person has a higher chance of surviving longer. So this function, as you can see, it follows exponential survival model. So that is a common assumption. In the, as I told you, three things are there: reliability engineering and insurance calculation and survival analysis. And in all cases, this uses the exponential survival model. And accordingly, we can decide the thing.
Okay.
Okay. So now if we see a sum, say question or example, suppose we have a 30-year-old person. Okay, so here you can denote x is 30 and the force of mortality is constant. Is constant at mu is equal to 0.02 per year. Okay. Now, if I tell you that we want to find the probability that this person survives for the next 10 years. So that is 30. So then to age 40. So how I will find it out? So here you can see the answer will be, since mu is constant. Okay. So we will use the simplified, last line only I told you that here we consider that it is constant. So we will use the simplified survival probability formula. That is TPX is equals to E of minus mu t. Now here you know what is mu, 0.02. And what is t? T is 10 years. So it is exponent. So how I will find out? I will put 10 T 30. That is e to the power minus 0.02 multiplied by 10. So that is e to the power minus 0.2.
Yeah.
So the calculation will come around 0.8187. Okay.
Yeah.
So what is the thing? The probability, if you see the question, that the person survives from age 30 to 40 is 81.87%. So there is a 81.87% chance that the person will be still alive.
Okay.
And if I say you that conversely, the probability of death, say within 10 years, then how it will look like? Obviously, it will be 1 minus 10 P30. Okay, so that means 1 minus 0.8187. So that percentage, it is coming around, how much it is coming?
0.1813.
0.1813. Yes. So that means that there is an 18.13% chance that the person will not survive until age 40. So if for the same question, consider what if I wanted to calculate the probability of surviving from age 30 to 50. Then how I will calculate?
The same but with 20 years?
Exactly. So using the same formula, only it is 20p30. So 0.02 multiplied by 20. And that comes to around e to the power minus 0.4. So that is around 0.6703. So that means the probability that the person lives until age 50 is 67.03%. And similarly, probability of dying before 50, that is the way I told you,
1 by
the
1.
inverse. So 1 minus 0.6703. So that is 0.3297. Okay.
Yeah.
So here the survival probability declines. You can know that the survival probability, it declines over time. Say for different mortality rates. So say lower mortality rate. If I consider that there is lower mortality rate, that means 0.01 being mu. So then how my curve will look like? The curve declines slowly. Mortality rate is 0.01. So that means higher survival chances over time. This is one. Now, if it is medium mortality rate, these interpretations are important. That is mu is 0.02. That means the survival probability decreases moderately. And if there is higher mortality rate, say mu is 0.05, that means the curve will drop. How much? Slightly. Means faster decline in survival probability. So from this you can show that a higher force of mortality, that is mu, leads to a faster decline in survival probability. Okay.
Yeah.
Hello, you can hear me?
Yes.
Yes, yes. Okay. Now here you have a image. You can see you are on the same, like there are certain assumptions.
Yeah.
Yeah. So I am on the same page. So how to do that? Okay. So let's understand them. So it is statistical assumptions in survival analysis.
Okay.
Statistical assumptions in survival analysis. So whenever we do any analysis, we have certain pros and cons.
Okay.
And certain criteria. So we have to understand that. So survival analysis, which you did, it often relies on what? It relies on Markov jump process. Okay, that means individuals move from one state. What is the state? From alive to dead. And that is based on what? That is based on transition probability.
Okay.
So that is based on transition probability. So here I am telling you this is hypothetical. So to make valid statistical inference, because why you are doing this? You want to make some analysis. So to make it valid and to clear for this inference, we will assume first fixed population size. Fixed population size. So that means we are observing n individuals, okay, over a finite time period. So that is from age x to x plus 1. This is, and how n is treated? N is treated as a fixed number. Okay? Means it is not a random variable. So it is not a random variable. And say how to determine it. Say if we analyze the survival of say 1000 individuals, if we want to analyze say in a medical study. So what we will assume? We will assume that we are working with a fixed sample size and the value being n is 1000. Okay.
Yeah.
Now second point, retrospective data analysis. Okay. So say instead of following individuals in real time, instead of following individuals in real time, that is prospective analysis, we study historical survival records. And what type of example here? If we get, it will be, say, instead of tracking patients, say, for the next 10 years, we use hospital records to analyze past patient survival trends. Noted?
Yes.
Now, third point. So, what is the third point? No simultaneity. Or you can say full year observation required. So that means that is we do not assume that all n individuals are observed at the same time. And we do not require that each individual was observed for exactly one full year. How the example will come here? So it will be like, if a study follows a group of patients from different hospitals. So some may have been observed for a few months, while other for several years. This is one. Now, independence and identically distributed. Independence and identically distributed. So that means each individual's survival is independent of others. And all individuals will follow the same stochastic process. That means that is, they have the same probability distribution of survival and mortality. So here you can take the example, say, if you want to analyze the lifespan of heart patients. So analyze the lifespan. You're telling something?
No, no, no.
Okay. Of heart patients. And we assume that each patient's survival is not influenced by another patient's condition. Okay. Now fifth one. Till fourth we have done. Now that is same transition probability for all individuals. That means since survival follows a Markov jump process. So all individuals share the same transition probability. So here what will be my example? Say if the probability of dying within a year at age 60, say 0.02. So then it applies to all 60-year-olds in the data set. So now these are the assumptions. So
Can
if
I
you,
see the screen a bit before?
okay, till this much,
Yeah, a bit up.
okay. Fourth point,
No, the fifth point.
fifth point only, okay.
Yeah. No, just a little bit. The last line is what I'm missing. The example.
Okay. Note it down.
Yeah. Yeah, done.
Done?
Yes. Done, ma'am.
Yeah. Okay. So these are the 5 points or the 5 assumptions which we are following for the same. So now based on this, these are the assumptions for statistical analysis, because as I told you that we are not concerned with the means when we are given a data, we have to analyze that. And for the same analysis, we need some data because there are certain pros and cons. And if we follow them, then only we can do it correctly. Now, estimating the survival probability using observed data. How we will do that? So, estimating the survival probabilities using observed data. So, how I will do that? So, let's see how we use this real world. So, we have studied maximum likelihood estimation.
Yeah.
Maximum likelihood estimation. So that is MLE. So the most common statistical method for estimating this survival probability is MLE. Why? How it works? It works by it calculates the likelihood function for observed survival data. And second, finding the parameter values. So that means mortality rate, say mu, which maximizes the likelihood function. Okay. So
Yeah.
suppose you have observed D dates. So for example, if we observe D dates among n people in a given year, so we can, till that noted,
Yes.
estimate the mortality rate mu using mu hat, that is d by n. So what does that mean? Mu hat, so where mu hat is the estimated mortality rate. Always hat means estimated. D is the number of deaths and n is what? Total number of observed individuals. This is your first one. Now you have more ways. So the second one coming to Kaplan-Meier estimator. Kaplan-Meier estimator. This is non-parametric.
Okay.
Non-parametric. So say if we have sensor data, that is some individuals are still alive at the end of the study. Suppose. So then we will use this Kaplan-Meier estimator. How it looks like? It looks like S hat T is equals to pi, and it will be I representing less than T. So 1 minus di by Ni. So that means where ST is what? Estimated survival probability at time T. And what is DI? DI is number of deaths at time TI. And Ni is the number of individuals at risk just before T. Okay. So this method is basically used in clinical trials and methodological study, medical study. Now, what you learned here, the real world application goes for every time for your life insurance, like you are predicting more debt. So accordingly, you can do and expecting the life, you can decide that.
Mm.
In medical research, as I told you, this formula estimating patient survival rates and reliability, like predicting and okay. Now the next slide here, how this data will be used in survival analysis, if we want to know that.
Yeah.
So here they have given the Kaplan-Meier estimator. So here, if you say, just note down the point, say how this data is used in survival analysis. So what is the survival time? It represents the number of years an individual was observed before either dying or being censored. Okay. So what will be the event indicator here? So here the event indicator will be death and censored. So one, if I consider death, that means the individual died during the observation period. So during the observation period. Okay. And zero. Zero means censored. So that means the individual was still alive when the study ended. So if this is the data set, you can use the Kaplan-Meier survival curve, or you can perform MLE based mortality rate. Okay. Noted?
Yes.
So here, to understand that how the statistical framework for the survival observation we will now analyze survival data using Markov jump process. And you know, it tracks individuals from the moment observation start until it ends. So say for each individual I, and you can take I being 1, 2 till m. So what it will be? First x plus, that is age observation, when age observation starts.
Mm.
When observation starts. So here you know that this is the age at which the observation starts. So it will vary across individual depending when they entered the study. So you can see that here the example might be a patient might be enrolled in a medical trial, okay, at 50, and while another at 55. So accordingly we can do. So this is one. Now second, what it will be? Second will be x plus bi. That means age when observation stops. That means this is the age when observation ends. So basically the study naturally concludes, say, after 1 year. The study concludes after 1 year. Okay. And the individual leaves the study early. Say, the individual leaves the study early. So the individual dies before the study, and it can be.
Okay.
Third, x plus bi constants. What is that? So here you consider till this point clear.
Yeah, clear.
So suppose observation end age is x plus bi, which I have taken. So x for this case, x plus 1 is if the study covers exactly 1 full unit period. This is one. And earlier than x plus 1 if the study ends before the full period. So it is equal to the individual's age at death if they die before the study ends. And also, as I told you. So why does this framework matter? Why does this matter? Yeah. So this framework, you're telling something.
Mhm.
This framework is crucial because it helps us handle right censored data. Okay. What is right censoring? Right censoring occurs when an individual when an individual survives beyond the study period. That is, we don't know their exact time of death.
Yeah.
And it also ensures that we correctly estimate mortality rate using MLE, that is maximum likelihood estimation. And it is widely used in actuarial science, which I have told you. Okay. So how it will work? There will be a data. Suppose you are conducting an analysis. Okay. So suppose example, let's say we are conducting a 5-year survival study. Okay. Say for a group of cancer patient. Okay. So I have told you that there are starting point and there can be different starting point. So here, if I consider, say, give patient ID and it is start age. Start age is X plus AI. And there will be end age also, that is X plus DI. And the status. So for patient 1, it is 50, it is 55. For 2, it is 52, 57. For 3, it is 49, 54. Plus 4, it is 51, 53. And for 5, it is 50 and 55. Okay. So here the status, if I consider,
Mm.
so here if I consider, it is alive, that is right censored. This interpretation only you have to understand. Died, alive, and alive means right censored. Died, and here alive. So what we understand from here? We understand that, noted the table?
Yes, yes, I did.
So patients 1, 3, and 5 were still alive at the end of the study. Meaning their data is right censored. That is, we have to interpret. And right censored, I hope you have understand by now the interpretation.
Yeah.
And patients 2 and 4 died during the study. So we have their exact survival time.
Mm.
And here what I will use? M, L, E. And using this, we estimate the mortality rate using this. So this is the way we can do the estimation and we can analyze from the two.
Okay.
Okay.
Mm.
Next, you are having understanding the death indicator variable. That means D of I. So what is that? The Markov jump process model tracks survival over time. That means to analyze the death occurrences. So we will use a statistical indicator variable. So here, if you want to understand what is the D, I told you the death indicator. So what is the D? What is DI? So DI is a random variable that tells us whether an individual death was observed. during the study period. So here you can say DI is 1 and 0. 1 means if the ith life is observed to die, and 0 means if the ith life is not observed to die. So from this, what you can say, if DI is 1, that means the person died within the observation on within the observation window, the frame. And if the DI is 0, that means the person was still alive when the study ended. So that means right censored data. This right censored data is very important. As
Okay.
I told you already, you can understand and you can interpret accordingly. So
Yeah.
I told you that it is right censored data of different type, or you can within the time frame. So accordingly, MLE you are using.
Okay.
So here from this, what you can understand that it helps us to determine which dates contribute to ST mortality rate.
Mm.
So this helps us determine which deaths contribute to estimate mortality rates. Okay. Then we have to do the expected value of D. That will come like 0. P of DI 0 plus 1. P of DI is 1 is equal to P of DI is equals to 1. Okay.
Okay.
So here this estimation is the expected value of DI. Like we know that there is probability associated with it, and accordingly we can find out, we can give the data and we can find it out. So if you are being questioned, so the expected value will be calculated like this. And here, since P of DI is 1, what it represents? It represents the probability of death occurring during the observation window.
Okay.
Okay. Okay. So today till this much. Next day again we will continue. Okay.
Yeah.
Thank you.